Yeah, okay, so we don't need to go back to winter. There's 7 of us. We have a lot to say.
Got it.
We're
Okay.
not gonna, we can't afford that time. All right. And in fact, I want to encourage all of you to follow up by email. My name's Vivek Goyal. My email address is goyal@bu, and you see how to spell Goyal on the screen right now. I'm excited to talk to you a bit about the field of computational imaging and my group's work in that field. So this slide gathers some representative images from several papers to give a sense of what we do. The first 3 columns are about 3D imaging with single photon detectors. Each of these contrast in the first row some conventional processing of some data, and then what we're able to do with the same data or in the same setting, and some kind of comparable setting. Then the last column shows images from our projects on seeing around corners. At the top, we have a method that can look through a small opening at an oblique angle and produce a reconstruction of a hidden volume. And at the bottom, we have a method that can take an ordinary digital photograph of a blurry partial shadow and form a reconstruction of what's outside the field of view that produced that blurry shadow. So to make this slightly interactive, even though I'm not really seeing all your faces, but to give you a little tiny bit of something to think about. Here's an ordinary digital photograph of beautiful Marsh Plaza at Boston University. How many photons do you think were sensed by the camera to produce it? I don't know the answer, of course, but I think it's a lot. I think I can guess within a couple of orders of magnitude. So I want to invite you to guess. And I'll tell you that I would guess 4 trillion based on a plausible calculation given here. If the camera has 4 million pixels, that means that you're detecting 1 million photons per pixel. It's not surprising that 1 million photons per pixel carry a lot of information and you can form sharp images and not even really need to think about the idea that photons are discrete. But one of my group's main interests is in direct time-of-flight LiDAR using far, far fewer detected photons. And there, we get a lot of advantage from thinking about the fact that light comes in quanta. They come in photons. So in a direct time-of-flight LiDAR system, laser pulses are directed towards a scene, and you can infer the distance of a scene patch and the reflectivity of that scene patch from a received signal. I showed you that the ordinary digital camera was operating at around 1 million photons per pixel. The kind of challenge that we like to look at is, what if you're only detecting around 1 signal photon per pixel? And maybe that's buried in around 20 times as much ambient light. Then your problem really requires a lot of interesting modeling, mathematical analysis, and algorithm development to lead you to the computations that you'll make to form depth and reflectivity images. Computational imaging as a field addresses a lot of different modalities. Within my group, I mentioned LiDAR. We also work in non-line of sight imaging. We've started working in passive thermal imaging, where you try to be able to see well enough to navigate an autonomous vehicle absolutely in the dark. Now, is the world ever really completely dark? Well, no, there are thermal emissions at certain wavelengths, and maybe those ambient thermal emissions are enough to be able to navigate an autonomous vehicle. And most recently, we've started picking up on projects in particle beam microscopy. All of these give opportunities to innovate in concepts, experiments, modeling, analysis, algorithms. It's really an end-to-end system development, and so you can pick up on whichever aspects interest you the most as the target of your work. So the way we work fundamentally is we just follow whatever we think are exciting ideas. I didn't start working in computational imaging in grad school or at Bell Labs or in my first startup. I worked on information representation, but that eventually drew me to computational imaging because I found that the central ideas of efficient representation of information could lead to innovations in computational imaging. So in my group, we do math, not really to prove theorems, but math more to derive algorithms and to understand how well different systems can possibly perform. We do real proof of concept experiments, and most importantly, we really have a lot of fun. I think that it is an absolute gift that your job can be to be creative, you know, and that's what, if you go into academic research, it means that that's your job, just be creative. And we definitely enjoy that. We enjoy each other. I'll mention, I don't know if Allison would like me to mention this or not, like Allison's group, they will go and throw axes. In my group, I really want to go do that sometime. We have not gone and thrown axes yet. We've won pub trivia multiple times at a local pub. And during the pandemic, we couldn't do those sorts of things. So we took a dumpling making class together. So I'll cede the floor here. I have to go teach my class. I'm not going to answer questions. I mean, I guess I'm not looking at the chat right now. I could answer questions really quickly now, but in fact, I think it makes more sense for you to send me questions by email because there are 7 of us to speak and I should go teach my class, but thank you very much.